Welcome to this walkthrough of LeetCode problem number 1842, next palindrome using same digits. In this session, we'll explore how to find the next lexicographical palindrome using the same set of digits as the input. Stay tuned as we break down the problem, discuss the approach, and analyze the solution step by step. In this problem, you are given a numeric string n composed of digits ranging from 0 to 9. The goal is to determine the next smallest palindrome that can be created using the exact same digits as n. If it's not possible to create such a palindrome, you should return an empty string. A palindrome, as a reminder, is a number that reads the same forward as it does backward. For example, 121 or 3443 are palindromes. The input will be a non-negative numeric string of length between 1 and 100,000, and the output should be a single string representing the next smallest palindrome, or an empty string if no valid palindrome can be formed. For example, consider the input n equals 1221. This input is already a palindrome, but the task is to find the next smallest palindrome that uses the same digits. The output in this case would be 2112. Because it is the next valid palindrome that can be formed with the digits of n. Now take the input n equals 32123. This number is also a palindrome, but in this case, it is impossible to rearrange the digits to form a new palindrome that is greater than 32123. Therefore, the output in this scenario is an empty string. Another example is when n equals 4444. Here, the input is already a palindrome, and since all the digits are identical, the only possible palindrome that can be formed is the input itself. Therefore, the output is 4444. These examples highlight how the function should handle cases where a palindrome exists, and where it does not. Let's also keep in mind the constraints. The length of n can go up to 100,000 digits, and the string will only consist of numeric digits, with no leading zeros unless it is the single number 0. Finally, let's consider some edge cases. If n is already the largest possible palindrome that can be formed with its digits, the output should be an empty string. For instance, if n equals 987789, there's no greater palindrome with the same digits, so the output is. If n has only one digit, it is trivially a palindrome, such as n equals 9, which would return 9. Similarly, if all the digits in n are the same, like n equals 1111, then the input is the only possible palindrome, so the output remains 1111. Lastly, if it is impossible to rearrange the digits into a palindrome at all, such as n equals 12345, the output is also an empty string. These cases provide a complete understanding of how to handle the problem under different scenarios. To solve the problem of finding the next palindrome using the same digits, we considered multiple approaches. First, let's look at the brute force method. In this approach, we generate all possible permutations of the digits in the input string, then filter out the ones that are palindromes, and finally, identify the smallest palindrome that is greater than the input. While this method is conceptually straightforward, the computational cost is prohibitive. Generating all permutations has factorial time complexity, and verifying each one adds even more overhead. As the length of the input increases, this approach becomes infeasible, which is why we rejected it. Instead, we turned to a more optimized solution. By leveraging the next permutation algorithm and focusing only on the first half of the string, we can drastically reduce the search space. This builds upon the symmetry property of palindromes, which makes a more efficient solution possible. The optimized approach begins with checking whether the input string is already a palindrome. If it's not, we immediately return an empty string. Next, we extract the first half of the input number. Using the next permutation algorithm, we compute the next lexicographical ordering of this first half. This step is crucial because it ensures that we are systematically moving to the next possible configuration. Once the first half is updated, we mirror it to reconstruct the full palindrome. If the input number has an odd length, the middle digit remains unchanged during this process. Finally, we validate the constructed palindrome to ensure it is greater than the original input. If it meets this condition, we return it, otherwise, we return an empty string. This approach is efficient, running in linear time relative to the length of the input, and avoids the high computational cost of generating all permutations. Now, let's break down the chosen strategy in more detail. The primary insight here is that palindromes are symmetric, so instead of working with the entire string, we focus on just the first half. This drastically reduces computational overhead. The next permutation algorithm plays a pivotal role in finding the next lexicographical order for the digits in the first half. Once we have this new configuration, we mirror it to form the full palindrome. The steps are straightforward. First, validate the input to ensure it's initially a palindrome, then, split the string into its first half, and, for odd-length inputs, isolate the middle digit. After computing the next permutation, we reconstruct the full palindrome by mirroring the updated first half around the center. As a final step, we check if this new palindrome is greater than the input. If it is, we return it, otherwise, we return an empty string. This strategy combines efficiency with clarity, making it a practical solution. The chosen approach strikes a balance between efficiency and simplicity. By focusing only on the first half of the input, we avoid the exponential complexity of generating all permutations and instead use the next permutation algorithm, which operates in linear time. This makes the approach significantly faster than brute force. While it is more complex than the brute force method, the logic becomes intuitive once the symmetry property of palindromes is understood. However, there are trade-offs to consider. For very small inputs, such as strings with only 2 or 3 digits, the brute force method might be simpler to implement and sufficient for those edge cases. The key insight, or aha moment, in this approach is realizing that modifying only the first half of the string is both necessary and sufficient for generating the next palindrome. This realization, combined with the use of an efficient algorithm for permutations, results in a scalable and elegant solution to the problem. To tackle the problem of finding the next palindrome using the same digits as the given number, we start with 2 primary tasks. First, we need to verify if the input number is already a valid palindrome. A palindrome reads the same forwards and backwards, so if this property isn't maintained, we simply return an empty string since no solution exists. Additionally, we handle edge cases, such as when the input is too short to form a meaningful palindrome, like a single-digit number. Once these initial checks are done, the next step involves splitting the palindrome into manageable parts. Specifically, we separate it into 3 components: the left half, the middle character if the number length is odd, and the right half, which is simply the mirror image of the left half. For example, given the palindrome 12321, the left half is 12, the middle character is 3, and the right half, being the reverse of the left, is 21. This separation sets the stage for generating a new configuration that remains a valid palindrome while being lexicographically larger. Next, we focus on finding the next lexicographical permutation of the left half, as this is key to generating a larger palindrome. To achieve this, we employ the next permutation algorithm. Here's how it works. First, scan the left half from right to left to identify the first digit that is smaller than the digit immediately to its right. Let's call the position of this digit I. Then, find the smallest digit to the right of I that is larger than the digit at position I, and swap these 2 digits. After the swap, reverse all the digits to the right of I to ensure the result is the smallest possible arrangement greater than the current one. If no such permutation exists, meaning the digits are in descending order, no larger palindrome can be formed, and we return an empty string. Once we have the next permutation of the left half, the next step is to reconstruct the full palindrome. To do this, mirror the new left half to form the right half. If the original number has a middle character, include it between the mirrored halves. For example, if the updated left half is 13, the new palindrome becomes 13131, assuming the middle character is 3. Finally, compare this reconstructed palindrome with the input number. If it's larger, we return it as the result, otherwise, we return an empty string. The essence of this problem lies in integrating 2 key components: finding the next lexicographical arrangement of digits and ensuring the result adheres to the symmetry of a palindrome. The next permutation algorithm is efficient, processing the left half in linear time, which simplifies the task of generating the smallest possible greater arrangement. By leveraging the symmetry of palindromes, we reduce the computational workload, as only half of the number needs to be manipulated. Additionally, if no next permutation exists for the left half, this directly implies that no larger palindrome is possible, saving unnecessary computation. In terms of data structures, the problem is handled efficiently using strings to represent the input and arrays or lists for manipulating digits during the next permutation process. Comparisons between integers are used to validate that the reconstructed palindrome is indeed greater than the original input. This structured approach ensures both accuracy and efficiency in solving the problem. Analyzing the complexity of the solution, the time complexity is primarily determined by the next permutation algorithm, which operates in linear time relative to the length of the left half, denoted as O(k). Reconstructing the palindrome also takes linear time, making the overall time complexity O(k). Regarding space complexity, the algorithm requires O(k) additional space for storing and manipulating the left half of the number. Let's look at an example to solidify our understanding. For the input 12321, the left half is 12, the middle character is 3, and the right half is 21. Applying the next permutation to 12 results in 21. Reconstructing the palindrome gives 13,131, which is greater than the input, so we return it. Now consider 32123. The left half is 32, the middle is 1, and the right half is 23. However, no next permutation exists for 32, as its digits are in descending order. This means no larger palindrome can be formed, and we return an empty string. These examples highlight how the algorithm efficiently handles different scenarios. To solve the problem of finding the next palindrome using the same digits, we start by first checking if the given number is already a palindrome. We do this by comparing the string with its reverse. If it's not a palindrome, we simply return an empty string since no valid result can be computed. Next, we focus on the left half of the palindrome, as this half determines the structure of the entire number. We extract this left half by slicing the input string up to the midpoint. For instance, if the input number is 1221, the left half would be 12. Once we have the left half, we generate all possible permutations of its digits using the permutations function from the itertools module. To ensure we work with unique and sorted permutations, we convert the result into a set and then sort it. After that, we locate the current permutation of the left half within the sorted list of permutations. This allows us to determine the next permutation in sequence. If a next permutation exists, we construct it by joining the characters of the next permutation tuple. Otherwise, if no next permutation is available, we return an empty string. Now that we have the next permutation of the left half, we can construct the next palindrome. If the length of the input number is even, the next palindrome is formed by appending the reverse of the left half to the new left half. For example, if the left half becomes 13, the resulting palindrome will be 1331. On the other hand, if the input number has an odd length, we need to include the middle character to preserve the structure of the palindrome. In this case, we append the middle character from the original number between the new left half and its reverse. This ensures the resulting number is both a palindrome and uses all the same digits as the original input. Finally, the function returns the constructed palindrome, completing the solution. To solve the problem of finding the next palindrome using the same digits, we start by checking if the given input is already a palindrome. If it's not, we immediately return an empty string, as there's no valid next palindrome to generate. If the input is a palindrome, we then split it into its left half. This is done by taking the substring from the start of the input up to the midpoint. For example, if the string has an even length like 1221, the left half would be 12. For odd lengths like 12,321, the left half would be 12 again, excluding the middle digit. Next, we convert this left half into a character array so that we can manipulate it and find its next lexicographical permutation. If no such permutation exists, meaning we've exhausted all possible arrangements, we return an empty string. Otherwise, we use the updated left half to construct the next palindrome by mirroring it. For even-length inputs, we simply append the reverse of the left half. For odd-length inputs, we also include the middle digit before appending the mirrored half. To determine if the input is a palindrome, we define the helper method isPalindrome. It uses two pointers, one starting at the leftmost character and the other at the rightmost character. The method iteratively checks if the characters at these positions are the same, moving the pointers inward until they meet. If any mismatch is found, the method returns false, otherwise, it confirms the input is a palindrome. Now, to find the next permutation of the left half, we define the next permutation method. This starts from the end of the array and searches for the first decreasing element, which marks the point where the current sequence is no longer in descending order. If no such element exists, it means the array is in its last permutation, and we return false. Otherwise, we proceed to find the smallest element larger than this decreasing element to perform a swap, ensuring the next permutation is lexicographically larger. After identifying the element to swap, we locate the smallest element greater than it by iterating from the end of the array. Once identified, we swap these two elements using the swap helper method. This method simply exchanges the characters at the two specified indices. After the swap, the sequence following the swapped position is still in descending order, so we reverse this portion to make it the smallest possible arrangement. This is achieved through the reverse helper method, which swaps elements from both ends of the range until they meet in the middle, effectively reversing the order. With the permutation updated, we return true, signaling that a valid next permutation has been found. These utilities collectively allow us to construct the next palindrome by working with the left half of the original input. To solve this problem, we start with the input n equals 1221. First, we check if the input is already a palindrome. Since 1221 reads the same forwards and backwards, it is indeed a palindrome. The next step is to split the input into its left half. The length of the string is 4, so we take the first two characters, resulting in half equals 12. Now, we generate all unique permutations of this left half. The possible permutations of 12 are 1, 2, 2, 1, and when sorted, they remain 1, 2, 2, 1. From here, we identify the current permutation, which corresponds to the arrangement of the left half in the original input. That gives us 1, 2, located at index 0 of the sorted list. To find the next permutation, we move to index 1, which is 2, 1. Converting this back to a string, we get next underscore half equals 21. Now that we have the next permutation of the left half, we use it to form the next palindrome. Since the input length is even, the palindrome is constructed by mirroring the next underscore half. This means we take next underscore half equals 21 and reflect it to produce the second half as 12. Combining these halves together, we get next underscore palindrome equals 21 plus 12 equals 2112. Hence, the final output for this example is 2112. Moving to the next example, we have the input n equals 1331. First, we check if it's a palindrome. Since 1331 equals its reverse, it is confirmed to be one. We then split the input into its left half. The length of the string is 4, so we extract the first two characters, giving us half equals 13. From here, we generate all unique permutations of 13. The permutations are 1, 3, 3, 1, and when sorted, they remain 1, 3, 3, 1. After sorting the permutations of the left half, we locate the current permutation, which corresponds to the arrangement of the left half in the original input. This gives us 1, 3, located at index 0 in the sorted list. To find the next permutation, we move to index 1, which yields 3, 1. Converting this permutation back to a string, we get next underscore half equals 31. With the next permutation of the left half identified, we proceed to form the next palindrome. Since the input length is even, the palindrome is constructed by mirroring the next underscore half. This means we take next underscore half equals 31 and reflect it to produce the second half as 13. Combining these halves, we get next underscore palindrome equals 31 plus 13 equals 3113. Thus, the final output for this example is 3113. In our third example, the input is n equals 999. First, we verify if it's a palindrome, and since 999 equals its reverse, it is confirmed to be one. Next, we split the input into its left half. The string length is 3, so we extract the first character, giving us half equals 9. Now, we generate all unique permutations of 9. Since there is only one character, the only permutation is 9, which is already sorted as 9, From this, we identify the current permutation, which corresponds to the left half in the original input. This is 9, at index 0. However, since this is the last index in the sorted list of permutations, there is no next permutation available. As a result, it's not possible to form the next palindrome using the same digits, and the output for this example is an empty string. The time complexity of the solution involves analyzing several steps. First, we check if the input string is a palindrome by reversing it and comparing it to the original. This reversal operation takes O(m), where m is the length of the string. Next, extracting the left half of the string using slicing is another O(m) operation, as slicing involves copying the characters. Then comes the critical step of generating permutations of the left half. If the left half has k characters, the number of permutations is k factorial, or k. Generating all these permutations requires k*k time, and since each permutation is converted into a tuple, there's an additional k cost for each. Together, this makes the cost for generating permutations k*k*k. These operations form the foundation of the time complexity analysis. Sorting the generated permutations is the next major step. Sorting a set of unique permutations takes p*log p time, where p is the number of unique permutations. In the worst case, p equals k, so sorting costs k log k. After sorting, we need to find the index of the current permutation in the sorted list, which takes p time or k in the worst case. Finally, constructing the next palindrome by concatenating strings involves m time. When we combine all these steps, the dominant factors are the permutation generation and sorting steps. This results in an overall time complexity of k*k*k plus k log k. Since k equals m divided by 2, we can rewrite the complexity as m/2 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 plus m/2 log m/2. The space complexity of the solution depends on several factors as well. First, the storage required for permutations dominates the space usage. Generating all permutations of the left half requires k*k space. Here, k is m divided by 2, and the k term reflects the factorial growth in the number of permutations. Sorting the unique permutations also requires p space, where p equals k. Additionally, operations like slicing the string and constructing the palindrome involve m space. When we combine these factors, the space complexity is primarily dictated by the storage of permutations, resulting in k*k. In terms of the input size m, this translates to m/2 m/2. To better understand the efficiency of the optimized approach, we can compare it with a brute force solution. The brute force method involves generating all possible palindromes using the digits of the input string and identifying the smallest palindrome greater than the input. This requires generating all permutations of the input string, which takes m. Filtering out non-palindromes adds m*m time, and comparing valid palindromes to find the smallest one introduces an additional q cost, where q is the number of valid palindromes. This results in a total time complexity of m plus m*m for the brute force method, which is significantly higher than the optimized solutions m/2 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 plus m/2 log m/2. Similarly, the space complexity of the brute force approach is m compared to m/2 m/2 for the optimized one. In the best case, where the input is not a palindrome, the optimized solution quickly returns with m time and 1 space, while the average and worst cases follow the previously analyzed complexities. The mathematical justification for the time and space complexities lies in the factorial growth of k, where k equals m divided by 2. Both generating and sorting permutations involve factorial operations, which grow exponentially as the input size increases. While the sorting step includes a logarithmic term, log k, this growth is negligible compared to the rapid increase of k. As a result, the factorial growth of m/2 dominates the overall complexity. This explains why the solution's efficiency is heavily influenced by the length of the input string, particularly its left half, making the factorial cost the key driver of both time and space requirements. When working on the next palindrome problem, there are a few common mistakes to watch out for. First, misunderstanding the palindrome property is a frequent issue. Some assume that any rearrangement of the digits, as long as it's greater than the input, qualifies as a valid solution. However, this is incorrect because the output not only needs to be larger but must also adhere to the symmetry of a palindrome. Then there's the mistake of ignoring edge cases. For example, single-digit inputs like 9 or strings where all digits are the same, such as 111, often don't have a valid next palindrome, and failing to account for this can lead to errors in your implementation. Another common pitfall is misusing the next permutation logic without considering that a palindrome requires symmetry. Simply applying the next permutation to the entire string won't necessarily produce a valid result. Lastly, inefficient computation is another trap. Generating all permutations of the digits and filtering for palindromes leads to factorial time complexity, which is impractical for larger inputs. Instead, solutions should aim to leverage the problem's specific constraints for better efficiency. Another potential mistake is overlooking non-numerical constraints. Many assume the input will always be a well-formed numerical string, but this can lead to crashes or undefined behavior if the string contains non-digit characters. It's crucial to validate the input to avoid such issues. Now, when it comes to interviews, there are some important insights to keep in mind. A key pattern is focusing on the first half of the palindrome. Since the second half is a mirror of the first, determining the first half uniquely defines the entire palindrome. In terms of trade-offs, balancing correctness and efficiency is vital. While brute force methods may guarantee correctness, leveraging symmetry can significantly cut down on unnecessary computations. Additionally, communication is critical in interviews. Clearly explaining how you enforce the palindrome property while finding the next permutation is often more important than rushing to complete the solution. A useful optimization tip is to apply the next permutation algorithm to the first half of the digits and then mirror it to construct the next palindrome. This approach combines efficiency with clarity. This problem also shares concepts with other related problems on LeetCode. For instance, LeetCode 31, Next Permutation, introduces the core idea of finding the next lexicographical arrangement, which plays a central role in solving this problem. Then there's LeetCode 5, Longest Palindromic Substring, where understanding the structure and symmetry of palindromes is foundational. Similarly, LeetCode 266, Palindrome Permutation, focuses on determining whether a string can form a palindrome, which ties closely to the validation step in this problem. Finally, LeetCode 267, Palindrome Permutation 2, extends this concept by generating all possible palindromic permutations, which aligns with the idea of constructing valid palindromes using specific constraints. Exploring these related problems can deepen your understanding of the techniques and principles involved. When considering alternative approaches to solve the next palindrome problem, there are a few trade-offs to evaluate. The brute force approach involves generating all permutations of the digits, filtering for palindromes, and selecting the smallest one greater than the input. While this guarantees correctness, it is highly inefficient with a factorial time complexity, making it impractical for large inputs. A more optimized approach involves applying the next permutation algorithm to the first half of the digits and then mirroring it to form the palindrome. This method is significantly more efficient, operating in O(n), but it requires careful handling of edge cases, such as when no next permutation exists. Another possible strategy is recursive backtracking, which explores valid digit placements to build palindromes dynamically. While this can handle constraints flexibly, it tends to be slower than the optimized approach, especially for larger inputs. Each method has its strengths and weaknesses, so selecting the right one depends on the specific constraints and requirements of the problem. Great job following along. We reviewed the problem, discussed the algorithm, and highlighted the key concepts. Palindrome problems are great for honing your understanding of symmetry and permutations. Be sure to practice similar challenges, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!